Good morning to one and all. Myself R. Sridhar, Assistant Professor of AAA Department, SRM University, Katangulathur. I am here to give you a lecture on Introduction to Photovoltaic System. As you all know that there is a glooming power crisis across the globe. Therefore, there is huge attraction towards renewable sources. Among all the renewable sources, photovoltaic and wind energy conversion systems are so emerging. Especially photovoltaic has a clear edge over other renewable counterparts. The reason for that is the scalable and portable structure, which is not that conducive in other renewable sources, makes it more prominent. Therefore, this lecture on photovoltaic system may cater the need of may kindle the interest among the students and also the fellow faculty and research people. So, whole of my presentation will be dealing with history of photovoltaic and the prevailing power scenario and what are the necessary components of PV systems, classification of PV systems, essentially the PV characteristics and the impact of insolation and temperature upon the PV characteristics, and what do you mean by MPPT, which is an indispensable component in any PV photovoltaic power system. And I also, before concluding, I also will deal with a particular application where the photovoltaic source will act as a prime component. Let me get into the lecture. So, photovoltaic system has a history of 180 years. Though it is so fascinating in present scenario, the research on photovoltaic actually began in 1839 when Becquerel introduced the photovoltaic effect in the year 1839. He used two electrodes and exposed to sunlight. As a result of that, electricity is produced. In 1873 and 76, William Gurriel and his students did a remarkable invention in finding out that when selenium is exposed to solar irradiation, it exerts current. The first solar cell was introduced in 1883 by Heinrich Hertz, and Planck and Einstein did enormous contributions to photovoltaic effect. In 1916, a scientist known as Robert Millikan evidenced the photovoltaic effect experimentally on Albert Einstein's published paper on Albert Einstein's paper, which was on 1905. The solar power was predominantly used initially in the space shuttles, where it is used to charge the batteries. After 1970s, the deployment of photovoltaic power system picked up. The developed nations invested a lot in the renewable source called photovoltaic. In 1991, in the evolution of photovoltaic system, there was a major breakthrough when George W. Bush, then President of US, established a National Renewable Energy Laboratory. This National Renewable Energy Laboratory, called NREL, is the source for so many research that happened in a photovoltaic power system. So over the past, in near future, lot of research, lot of development has happened in photovoltaic power system. So photovoltaic power system, what we use, has a history of 180 years. Let us see the world PV scenario. As you all aware that all developed and developing nations are showing much interest in deploying photovoltaic power system. If you notice the bar diagram, nearly 400 gigawatt has been installed all over the world in 2017, and the deployment of photovoltaic system is exponentially increasing. The Asian counterparts like China, they are much into the system, they have a pragmatic target of 50 gigawatt each year. So this is the way that PV scenario is exponentially increasing across the globe. In India, we have a ministry, separate ministry, which encourages renewable energy resources deployment. We also have National Institute of Science Solar Energy, NICE, which encourages investments in solar. In India, the total installed capacity in India is on October 2017, we have 3,31,000 megawatt, out of which the contribution by solar power is nearly 3.8%, which is 12 gigawatt. There are so many types of PV systems. Depending upon the connection of the load interfaces, we can classify the PV systems. We can classify the PV system into standalone system. We can classify it as grid connected systems. We can also classify that into hybrid power systems. When I say standalone systems, so standalone systems serves for a standalone load which is not connected with a grid. The example that has been shown in the photo that shows a PV panel which is connected directly to PV array directly connected to water pumping systems. This is a standalone load. So that is why it is called as standalone system. Another good example for standalone system is, imagine a traffic light controller which has a PV and a battery, and it feeds power for the LED lamps. So no connection with the grid utility. That's why it is called as standalone systems. Next is the grid tie systems. Generally, the grid tie systems will be in larger power rating. So there will be PV farms, in other words PV array, which will be connected to existing grid utility system. The PV voltage will be exported to the grid voltage. Next is hybrid systems. So hybrid systems embodies two or more sources along with PV. That's why it is called as hybrid systems. In the photo that is shown, we are seeing a PV panel along with wind electric conversion systems. The wind electric conversion system and the photovoltaic system are a good blend. The reason is they are little complementary sources. Approximately on a gloomy day, the wind will be more, and on a sunny day the wind will be less. So these two sources complements in nature. Therefore, this is a good blend of hybrid systems. Not necessarily always wind electric conversion system should be connected with photovoltaic system. It can also be interacted with other sources like fuel, diesel generator likewise. This particular slide explains you the PV array interacted with loads. PV as such consists of photovoltaic cell. Photovoltaic cell is the fundamental unit of a PV panel or a PV array. The problem, the biggest hurdle that the PV array or a PV panel encounters is the intermittency problem. The output of the PV array is intermittent in nature. The reason for that is the power rating. The output power of PV array will vary depending upon your irradiation and temperature. Therefore, we need an interfacing controller before feeding to loads. Therefore, the power electronic interfaces are mandatory between your PV array and loads. In the slide, I have shown a DC load. PV as such is a DC load which is going to get interacted with a DC load. Therefore, to regulate the PV voltage with that of the voltage of DC, we need a DC-DC voltage controller. That's why that controller is called as DC-DC voltage controller. And also, if you want to charge a battery, you need a charging mechanism so that the battery voltage is charged uniformly so that it will not get damaged. For that, we need a control mechanism for battery charging. So that controller also provide power regulation from PV as well, uniform and smooth charging of the battery. If your loads are AC, of course, PV being a DC, definitely it needs an inverter to make it into an AC load. Therefore, inverter is also there if you are interacting with AC loads or grid utility. You can also discard the usage of DC-DC controller and the power regulation mechanism you can do in the inverter itself. That is also possible. So this is a typical PV system. So this is the fundamental structure of a PV system. So there are huge research happening in PV cell manufacturing as such, improving the efficiency of the PV cells. So PV cell materials can be categorized into non-organic and organic. So silicon is the major component of the manufacturing in PV, can be classified into crystalline silicon and thin film silicons. So crystalline, monocrystalline, multicrystalline. Depending upon the manufacturing technology, depending upon the extract from an ingot, it is classified into monocrystalline and multicrystalline. Likewise, huge research is happening from the material science side for the PV, improving the efficiency of the PV. So in recent days, we are witnessing dye-sensitized solar cells also. In recent years, we are seeing solar cell which is flexible in nature, which can be found over the roof of a car or which can be pasted over the glass window in household. So likewise, a lot of research is happening in the manufacturing technology. So material science people, physics people, they are doing a lot of research in PV cell manufacturing to improve the efficiency. Over the years, a lot of research has happened and research papers have been achieved and the efficiency is increasing and the cost of the PV cell is reducing. So PV cell to array formation, as I was told already, a fundamental component of a PV photovoltaic system is a PV cell. Generally, a PV cell will be approximately equal to 0.6 volt and the current rating depends upon the size of the PV. After all, the current depends upon the irradiation or insolation. When I say insolation, it refers to the irradiation measured within a time frame, within hours, a monthly. That's why it is called as a word called insolation. So PV cells are connected in series and parallel to constitute a PV panel. So depending upon their rating, PV cells are arranged in series and parallel. These cells are arranged to form a module, and again these modules are again arranged in series and parallel to make it into a PV form. So you can see that a single crystal PV panel is shown and polycrystalline PV panel is shown, and you can, for the same size, monocrystalline panel gives you more wattage than the polycrystalline. The reason is that the efficiency of the monocrystalline silicon is slightly higher than that of the polycrystalline. Therefore, the output power is more than for the same size of a PV panel. Of course, the polycrystalline will have lesser cost compared to the monocrystalline. So next is very interesting part, the solar panel parameters. So students who are working in solar projects, they should be knowing the characteristic feature of solar panel, of course. Each solar panel will have specific data behind the panel. There will be a sticker which specify the specifications of the solar panel. So for example, in this 100 watt panel, you can see what is the maximum power, 100 watts, what's its open circuit voltage, and what is the short circuit current, and maximum power voltage of it, maximum power current, and maximum system voltage. So these data are taken for standard test conditions called STC. When I say STC, it refers to standard test conditions. What do you mean by standard test conditions? Standard test conditions are the conditions at 1000 watt per meter square. 1000 watt per meter square is the insolation or irradiation. So it can be called as suns also. 1 suns, the unit of irradiation is watt per meter square or suns. So 1 suns is equal to 1000 watt per meter square. And 25 degree centigrade. So the two parameters which are very crucial are the temperature and insolation. So the insolation is 1000 watt per meter squared and 25 degree C for the standard test conditions. So you can see an IV curve which essentially have the parameters whatever we are seeing in the data sheet, of course. The current and the voltage in the x-axis and current in y-axis. You can see the short circuit current. So short circuit current forms the upper limit in the y-axis. So when I say short circuit current ISC, that refers to the impedance less. The impedance value is so weak, so less. That's why this current is maximum called ISC. R is equal to 0. Next is the open circuit voltage, that is VOC, open circuit voltage. That means the impedance is at maximum. So if you draw a curve between ISC and VOC, then the curve that you got is called as IV curve. And also you can see there is a rectangular portion which is represented in dotted line, which gives you another two values respectively in y-axis and x-axis. One is called as the VMP, another one is called as IMP. So ISC is at the top, IMP is slightly lesser than ISC. Likewise, VOC is the right extreme where VMP is slightly in the left part of VOC. What does VMP and IMP refers to? VMP and IMP refers to the point at which maximum power is extracted for a PV panel. This is what called IMP and VMP. So generally the product of VMP and IMP, they will call it as Pmax. So when you see the specifications of the PV panel, you can see maximum power 100 watts. That means that the product of VMP and IMP. And VOC and ISC, the product of VOC and ISC definitely will be greater than that of VMP and IMP. But at the same time, if you look deeply into the curve, say for example, when ISC is maximum, your voltage value is minimum. When your voltage value is maximum, your current value is minimum. So when you product the voltage and current value, you can find that only at the maximum power point, which is nothing but the product of VMP and IMP, you will get maximum power point. So that is the point where you can get maximum possible power from a typical PV curve or IV curve, of course. So that is what called maximum power point. So the fill factor is an index of another index of the efficiency. Generally, efficiency will be called as efficiency is equal to P0 divided by the insolation G into the area. But pragmatically, the fill factor, talking in terms of the efficiency, talking in terms of fill factor is more reliable. So fill factor is equal to VMP into IMP divided by VOC into ISC. So denominator you have the product of VOC and ISC. In the numerator you have VMP and IMP. That's why it is called as fill factor. So in the right side of this slide we are seeing these so many methodologies how to measure the short circuit current and open circuit voltage. Of course, you can take this as an experiment in your class. Students can take a typical PV panel, whatever the immaterial of the power rating, they can take a PV panel and they can see the specifications. They can divide the VMP by IMP and they can fix the R value. By fixing the R value, they can appropriately take a potentiometer. They can connect across the PV panel, and when they move the potentiometer from lesser value to higher value, they can also plot this curve whatever we are seeing experimentally. So that is a small experiment that students can do in their classroom. That is what they have shown using multimeter. So the current measurement, of course, they can measure using a clamp meter or a multimeter. That's what it has been shown in this particular slide. So far I have told about the PV cell emerging into a PV array. So PV cell is the fundamental unit which forms into a PV panel, and arrangement of PV panels in series and parallel makes into PV array. In this slide you can see India's largest PV plant as of to till date. It is situated in Sivaganga district in Tamil Nadu, nearly 648 megawatt, which was commissioned in 2016 December. It is situated in Kamudi, exactly, we say. So PV panel available in market is from 2 watt to 250 watt. Generally 250 watt will be the maximum. At certain cases you can customize and get more than that also. But as a standard value, 250 watt is the maximum wattage available. So of course, I have divided 648 megawatt divided by 250 watt. So you can see 25 lakh panels probably will be available in the India's largest PV plant. So you can see the number of the PV panels. So maximum panel rating, each panel's rating may be of 250 watt. That's why I have divided 648 into 250. 25 lakh panels are available in that PV farm. So you can imagine the voluminous of the PV plant. Next important is we should see about the PV cell equivalent. So PV cell, in the right bottom of this slide, I'm showing you a typical PV cell, a monocrystalline and a polycrystalline. The right extreme is a polycrystalline, the left one is a monocrystalline, and you can see it is like a PN junction where the top layers are connected through a contact and exerted out and given as a cathode, and the bottom layer of the cells are formed as a anode. So positive and negative. The end user can take two wires from that and you can use it. So that is the photographic representation of a PV cell. The equivalent representation is PV cell is shown as a current source connected across a diode, and of course in a non-ideality cases we may have shunt and series resistance. The reason behind showing the PV cell as a current source is the current magnitude of a PV cell is directly proportional to the irradiation. If you take into account a 100 watt panel, you can see its VMP voltage will be 17.5 and the current will be more than 5 amps. Of course, the current rating is higher. Therefore, always the PV cell is represented as a current source. That's why in the left extreme, IP refers to a current source. So a typical PV curve is shown if there is no shunt resistance and series resistance. Probably the curve should be what we have drawn in shaded part as similar to a square. Because of the RSH, you have a dip in the current, and because of the series resistance RS, you have a dip in the voltage. That's why the curve is likewise. So this is decided by the ideality factor also. So the shunt and series resistance plays a crucial role in the output power of a typical PV cell. The another way of reasoning the PV curve, the IV curve, is current source I will have constant current, and the diode breakdown voltage will increase from the x-axis. So the output after the diode will have IP minus ID. So when you subtract that current, the waveform will be very similar to whatever we have got. So from this, what we infer is PV cell as such is neither a voltage source nor a current source. We can approximate that 70% it is more as a current source and 30% as a voltage source. This is an approximation. And given the equivalent circuit, students can realize this equivalent circuit in simulation environment, and they can extract these IV curves, and also they can model this as an equation modeling by writing the diode's saturation current equation, and by solving it with Kirchhoff's voltage law, this particular circuit, they can simulate and extract the IV curves. When I say IV curves, I may also sometimes say about PV curves. You should not get confused. We have I and V to form a IV curve. PV curve is nothing but power and voltage curves. Always when we have I and V, we can product that and we can draw power and voltage curves. Solar cell is a tricky source. Of course, it's a tricky source. The reason behind it is we cannot get constant output power from the solar cell. The reason is that the solar output voltage varies with respect to the given irradiation and temperature. So, as I have told already, the short circuit current represented in the left extreme and the open circuit voltage is in the x-axis. You can see that as irradiation varies, the IV curve's magnitude also varies. You can see in greener, the graphs given in the greener color, you can see 200 watt per meter squared. That means 200 watt per meter squared is the irradiation, and next is 600 watt per meter squared is the irradiation, and next is 1000 watt per meter square. In all these three curves, you can witness that the current and voltage values varies, and of course the output power also varies. You can see the short circuit current and the open circuit voltage slightly varies with respect to irradiation from this point. And also this curve, greener curve, has been given for a single solar cell. The same curves can also be extracted for any PV rating, which will be very similar. So this characteristic curves I have drawn as for a PV module. Earlier I have shown you for a PV cell. You can see for a PV module where the irradiation varies, the peak power also varies. So as irradiation varies, predominantly the current varies. When the current varies, the power varies. As the temperature varies, the thermal noise varies. and because of that the performance of the PV panel will deteriorate. You can see that in IV and PV curves, the open circuit voltage moves to the left side. The reason behind that is we should assume that there is an increase in irradiation as well increase in temperature. The effect of temperature and PV cell characteristics can be clearly indicated in the tricolor graph that I have shown you. T1 and T2 and T3. T3, imagine it is 25 degrees C. T2, you imagine 50 degrees C. And T1, you imagine 75 degrees C. So as temperature increases, your open circuit voltage decreases and your output power also decreases. As temperature increases, your ISC may increase to an extent, but at the same time, the difference in open circuit voltage makes the PV power to go very low. That's why you can see the greener line among all these things is among all these graphs, curves, PV curves. The greener one is having lesser power compared to other two. The reason behind is the temperature is high in the left extreme curve. So to summarize the characteristic curves performance, you should know that the irradiation and temperature plays a crucial role in determining the efficiency, power output of any photovoltaic panel or even cell or even array. So the inferences are: the power increases with increase in insolation, the short circuit current increases with increase in temperature, and the open circuit voltage, of course, reduces with increase in temperature. The power decreases with increase in temperature. And also, most importantly, you should witness that there exists a peak power in each curve. So as irradiation varies from 200 watt, 300 watt, 400 watt. If it is difficult to understand, you imagine a 100 watt panel may have only 30 watts at 8 o'clock. The same 100 watts panel may have 40 watts at 9 o'clock. The same 100 watts panel may have 80 watts at 11 o'clock. The same 100 watts panel may have 100 watts at 12 o'clock. So there should be a mechanism to see to that. We have to extract whatever maximum power available for that particular irradiation. The reason behind myself telling in time is for better understanding. So a typical PV panel of rating will not yield you constant output because your irradiation and temperature is varying. But at the same time, we should see to that your PV panel operates at a particular point called maximum power point, at which the PV panel is capable of rendering whatever power it possesses. So we need an intelligent mechanism to grasp that power. That is called as MPPT, maximum power point. So MPPT is an indispensable component in any photovoltaic system to make sure that the PV renders whatever power maximum available at a given point of time. Otherwise, if you do not have an MPPT system, probably we may end up in derating the PV power whatever you are having. Let me explain a case study to show why MPPT is an indispensable component. Imagine a 100 watts panel whose VMP is 17.5 and 5.71 is its ISC. So when you product that, approximately you may get 100 watts. And I have calculated my R load value to be the maximum or max, so that it will yield you Pmax. That means 17.5 divided by 5.7 will be my optimum RL, so that my PV panel will operate at maximum. In that way, I have found that my resistance value is 3.06. So when I have a resistance of 3.06, there is no such problem. I can extract the maximum 100 watts available. Imagine now my irradiation is halved. That means I'm getting 1000 by 1000 watt per meter squared divided by 2. That means 500 watt per meter squared is available in the irradiation. That means my current and voltage, there is chance for drooping. But here I choose the same resistance to prevail in the circuit. Therefore, my voltage drops to 8.99 and my current is 2.94. So when I product that, I am getting only 26 watts, where at 500 watt per meter square, my PV panel is capable of giving 50 watts. So obviously I am losing a 24 watts power if I am not using an MPPT system. So MPPT system is nothing but a system which will regulate your R0 with respect to your source voltage, or source resistance or Thevenin. You can equivalent this to a maximum power transfer theorem. So here I am using a series resistance so that my effective voltage is adjusted so that I get a 17 volts, so that I can get the remaining power wattage of 24 watts is yielded. So by adjusting my resistance, I am getting a 24 watt power what I lost. So the conclusion is, you should adjust your R Thevenin if your RL is fixed. How to change my R Thevenin? I mean the input voltage and current. How to change it? By changing the duty cycle of a DC-DC converter. So the series resistance, you have to equalize that to a DC-DC converter. The job of the DC-DC converter will be matching your source voltage and current to that of the load, so that maximum power, whatever power available in the PV panel, is exerted out. So these are the cases we are seeing it. For first case, you have 1000 watt per meter square. In second case, you have 500 watt per meter square, but the load remains the same. In the third case, I have an MPPT system. Here you can imagine that as a buck converter, since I have added a series resistance. So your DC-DC converter may be a buck converter or a boost converter or a buck boost converter, or whatever contemporary power electronic controller you can use. The bottom line remains the same. You are going to adjust your operating point of the PV panel at VMP or IMP so that maximum power is exerted to the load. A simple analogy also you can think, imagine a car drive system. So a car has 4 gears, and each gear have a stipulated speed value at which if the car runs will have maximum efficiency. So a car running at 60 km should be of third gear, 40 km maybe of second gear, first gear is of 20 km, and fourth gear is of 80 km. If the same car runs at first gear in 80 km, again you are losing the power. The same way, we have to see to that in a PV panel, you should have a power tracking mechanism that will match your load resistance value with that of the source resistance, so that maximum power is exerted. So that is what called MPPT system. So in a car, if you have a top gear with lesser speed or lesser gear with higher speed, obviously you have a power loss. Similar to that, in PV also, for each irradiation value, you have a power, and you have to extract that maximum power from the PV panel. So that is what called maximum power point tracking system. So maximum power point tracking is an online mechanism done by the combination of an intelligent algorithm called MPPT algorithm along with a DC-DC converter or inverter. So a power electronic interface along with an control algorithm is called MPPT system. So MPPT stands for maximum power tracking, and each solar cell has a point at which I and V will be maximum. The product of I and V will be maximum. We have to see to that the panel operates at this particular point for the given irradiation and temperature. So this is what called MPPT I have explained. So this is a typical block diagram of a MPPT aided PV system. We have a solar panel. We may have an MPPT controller block. We may have a DC-DC converter, and we can have a load. As I have already told, the DC-DC converter can be a buck converter, boost converter, buck boost converter. Probably that is depending upon the that selection depends upon the load and source voltages. Imagine you have 2 or 3 batteries of 12 volt. So 3 batteries of 12 volt will be of 36 volt. Imagine you are having a 100 watt panel. Approximately that will have a 17 volt as VMP. So you have to charge a 36 volt battery. Obviously you need a boost converter. If you have only a 12 volt battery, you can have PV panel of 100 watts and you can have a buck converter. So the choice of the DC-DC converter, which is going to be interface between solar panel and load, depends upon your load rating, of course. And there are numerous MPPT techniques available. Each has its own merit and demerits depending upon the application, depending upon the complexity involved in execution. So a lot of nuances is involved in framing an MPPT algorithm. So let me explain a typical MPPT algorithm called fractional voltage MPPT algorithm, which is a classical MPPT algorithm. Right. And this will be quite easy for students to implement it as a project, as well for a application like a pumping system. For a simple application, it is not necessary that students should use a more complex algorithm. An algorithm like fractional voltage MPPT algorithm or fractional current, short circuit current MPPT algorithm will be more conducive. So let me explain this fractional voltage MPPT algorithm. So you have a PV panel and you have a DC-DC converter and you have a load. This DC-DC converter is regulated by a PWM pulse or a duty cycle, and this duty cycle is nothing but a duty cycle exerted out from an MPPT algorithm. So this fractional voltage MPPT algorithm, see the PV curves, it resembles from the PV curve. You imagine a PV curve that has been shown here. On seeing the PV curve or IV curve, of course, you can see that the maximum voltage VMP hovers between the 0.7 to 0.8 of VOC. As a thumb rule, as an approximation, you can see whatever the changes that is happening in the irradiation or not, the VMP point lies between 0.7 to 0.8 of open circuit voltage. Therefore, you can hard code this value in your coding. This approximation can be implemented in an algorithm, and you can see to that your duty cycle is taken from your MPPT algorithm, which makes sure that your PV panel operates at a particular voltage VMP, which in turn makes the PV panel to operate at maximum power point. So this particular right hand side block diagram will explain you the algorithm implementation. So VM is the maximum voltage. So VM is nothing but a K times of VOC. Of course, K is 0.7 to 0.8 VOC, and VT is the actual voltage, and this Error is given to a PI controller. PI controller reduces the error, and then it is given to a comparator where PWM is generated. When the error from the PI is compared with the triangular pulse, you are getting duty cycle, and that duty cycle is given to the DC-DC converter. So this DC-DC converter duty cycle will make sure that your VT is operating at a point of VMP for that particular irradiation which delivers you the peak power. So this is what called fractional voltage MPPT algorithm. You can do fractional current MPPT algorithm also. So when you witness IV curves in my slides in the previous pages, probably you can witness that it is around 0.85 to 0.9 of ISC will be your IMP. So you can use that algorithm called fractional short circuit current MPPT algorithm. So these two techniques are very simple in nature. For an application like pumping, where the speed of the pump is not that much matters, so we can use, for a simpler application, we can use fractional voltage MPPT algorithm or short circuit current MPPT algorithm. So other prominent MPPT algorithms are there. Beethoven Observe, which is very attractive and it has been used widely. And next is a computer algorithm called incremental conductance algorithm, ripple correlation. You can implement AI aided, the artificial aided, intelligence aided MPPT algorithm like fuzzy and ANN, and of course. So more or less, more than 50 MPPT algorithms have already been achieved in research. So people who work on a photovoltaic system essentially should have a good knowledge in implementing MPPT algorithm. As I was told already, that MPPT is an indispensable component in a photovoltaic system. So let me conclude my lecture by showing you a typical PV application block diagram. So this particular block diagram is a bottom line of any particular project involved in PV. So PV arrays will have DC voltage, that's why it is called a DC bus filter. You can have a capacitor, buffer capacitor, which regulates the ripples in the PV voltage. Of course, in my previous slide, you would have seen I have connected a capacitor across the PV block. And you have battery banks. Not essentially your system should have a battery bank, but I have shown a battery bank. That battery banks should be charged with a control algorithm called battery MPPT charge algorithm. And this battery MPPT charge algorithm is connected to an inverter. And inverter, if it is given to a utility, which is nothing but a grid, of course, you should see to that the grid voltage, the profile of the grid voltage should match with that of the inverter. That's why we have an output filter. So the possible project area for students are defining the battery charger MPPT. First choice, they should select appropriate DC-DC converters and appropriate MPPT algorithm for battery charging. And next is appropriate choice of the topology of the inverter. There are so many inverters are available: multi-level inverter, a sine inverter. Like this, a lot of inverters are available. And of course, for giving pulses for the inverter, there is again a different research area. You have a lot of pulse width modulation techniques for firing the inverter. And next is the filter design and grid synchronization techniques. I have given here as a utility. To utility means it's a grid system. So when you are interacting with your grid system, you should have essential compliances or your voltage, frequency and your phase angle should match. So you should have a good grid synchronization techniques also. And not, of course, always you should connect to utility. You can also have a standalone loads. So when you want to have a closed loop operation of your standalone load, imagine a induction motor, you should also have a feedback from that closed loop and given to the inverter pulse. So this is a bottom line of a PV application. So whatever projects you do, 90% of the components here are indispensable. So with this, hope I'll conclude my lecture on introduction to photovoltaic system, and I believe that this would have kindled some interest among the students and fellow research people and faculties. Thank you one and all.